Let's clarify equipment grounding conductor requirements for electrical metallic tubing, or EMT, raceways in specific areas of hospitals according to the National Electrical Code, specifically Article 517.10b. This section addresses wiring methods for essential electrical systems in healthcare facilities. The question revolves around whether an equipment grounding conductor is required within EMT raceways that supply power to panel boards, lighting, and receptacles located in business offices and hallways within a large hospital. To understand this, we need to delve into the nuances of Article 517.10b and related sections. Article 517 of the NEC covers healthcare facilities. It outlines special requirements for electrical installations in these facilities to ensure patient safety and reliability of the electrical system. Section 517.10 specifically deals with wiring methods for essential electrical systems. Essential electrical systems are those systems that are crucial for patient care and safety, and they must remain operational even during a power outage. Now let's focus on the specific question about EMT in business offices and hallways. According to the NEC, the areas within a hospital are categorized based on their function and the level of patient care provided. Business offices and hallways generally fall outside of what are considered patient care areas. These areas are typically administrative spaces or corridors where direct patient care is not routinely administered. Because of this distinction, the wiring method requirements may differ from those in patient care areas. Section 517.10b allows for exceptions to the general rule of requiring an equipment grounding conductor in raceways. However, it is important to note that this exception is not universally applicable to all EMT installations in hospitals. It depends on the specific circumstances and the type of electrical system being used. Generally, for essential electrical systems in patient care spaces, a redundant grounding system is required, which means that both a metal raceway, such as EMT, and a separate insulated equipment grounding conductor must be installed. This provides an extra layer of protection against ground faults. However, in non-patient care areas such as business offices and hallways, the NEC may permit the use of EMT without a separate equipment grounding conductor, provided that the EMT itself is properly installed and provides a reliable ground path. The key here is that the EMT system must be installed in accordance with Article 250 of the NEC, which covers grounding and bonding. This includes ensuring that all EMT fittings are properly tightened and that the raceway system is continuous and electrically conductive. The exception in 517.10b hinges on the integrity of the EMT as an equipment grounding conductor. If the EMT system is not properly installed, or if there are any loose connections or other factors that could compromise its ability to carry fault current, then a separate equipment grounding conductor would be required. Also, it's critical to understand that the allowance of EMT without a separate equipment grounding conductor in non-patient care areas only applies to the essential electrical system. For normal power circuits in these areas, the general rules of the NEC apply, which typically require an equipment grounding conductor to be installed with the circuit conductors. The National Electrical Code provides detailed requirements for grounding and bonding in Article 250. This article is essential for understanding the specific rules that apply to EMT and other metal raceways. Some key requirements include ensuring that all metal raceways are securely connected to enclosures and equipment, using listed fittings and connectors, and properly bonding the raceway system to the building's grounding electrode system. To ensure compliance, a thorough review of the project specifications, electrical drawings, and the applicable sections of the NEC is required. It is also important to consult with a qualified electrical engineer or inspector who can provide expert guidance and interpretation of the code. Here's a breakdown of the key considerations. Firstly, determine whether the area in question, such as a business office or hallway, is considered a patient care area. This will dictate the applicable wiring method requirements. Secondly, ensure that the EMT system is installed in accordance with Article 250 of the NEC, which covers grounding and bonding. This includes using listed fittings, properly tightening connections, and bonding the raceway system to the building's grounding electrode system. Thirdly, if the EMT system is deemed to provide a reliable ground path and the area is not a patient care area, then it may be permissible to omit a separate equipment grounding conductor. However, this should be verified by a qualified electrical engineer or inspector. Fourthly, remember that the exception for EMT without a separate equipment grounding conductor only applies to essential electrical systems. For normal power circuits, the general rules of the NEC apply, which typically require an equipment grounding conductor. Fifthly, always consult with the authority having jurisdiction, or OJ, to ensure compliance with local codes and regulations. The AHA has the final say in interpreting and enforcing the NEC. Sixthly, proper documentation is essential. Keep detailed records of the electrical installation, including wiring diagrams, equipment specifications, and inspection reports. This will help demonstrate compliance with the NEC and facilitate future maintenance and modifications. In summary, while the NEC may allow for the use of EMT without a separate equipment grounding conductor in certain non-patient care areas of hospitals, this is subject to specific conditions and requirements. It is crucial to understand the applicable sections of the NEC, ensure proper installation of the EMT system, and consult with qualified professionals to ensure compliance and safety. The final determination of whether an equipment grounding conductor is required rests on a comprehensive assessment of the specific installation and the applicable code requirements. Always prioritize safety and compliance when working with electrical systems in healthcare facilities. It is also critical to understand the different types of grounding systems used in hospitals. There are two main types: isolated power systems and grounded power systems. Isolated power systems are typically used in critical care areas, such as operating rooms, to minimize the risk of electric shock. In these systems, the electrical circuits are isolated from ground, which means that a single fault to ground will not create a path for current to flow. Grounded power systems, on the other hand, have a direct connection to ground. These systems are more common in non-critical care areas such as business offices and hallways. The type of grounding system used will affect the wiring method requirements. For example, isolated power systems typically require special wiring methods to maintain the isolation from ground. Here are some additional points to consider when evaluating EMT grounding in hospitals. Firstly, the size of the EMT is important. The NEC specifies minimum sizes for EMT based on the ampacity of the circuit conductors. The EMT must be large enough to provide a low impedance ground path. Secondly, the type of fittings used is also critical. Only listed fittings should be used, and they must be properly tightened to ensure a reliable connection. Thirdly, the continuity of the EMT system must be verified. This can be done using a continuity tester to ensure that there are no breaks in the ground path. Fourthly, the NEC requires that all metal raceways be bonded to the building's grounding electrode system. This is typically done by connecting a grounding electrode conductor to the raceway system. Fifthly, hospitals often have additional requirements for grounding and bonding beyond what is specified in the NEC. These requirements may be based on industry standards or local codes. Understanding these additional requirements is essential for ensuring compliance. Sixthly, regular inspections and maintenance are critical for maintaining the integrity of the grounding system. This includes checking for loose connections, corrosion, and other damage. Any problems should be corrected immediately. Proper grounding is essential for protecting patients, staff, and visitors from electrical hazards. It also helps to ensure the reliable operation of medical equipment. When working with electrical systems in hospitals, it is always best to err on the side of caution and consult with qualified professionals. The consequences of a grounding failure can be severe, so it is important to take all necessary precautions. Finally, remember that the NEC is a living document that is updated regularly. It is important to stay current with the latest changes to ensure compliance. The National Fire Protection Association, or NFPA, offers training and resources to help electrical professionals stay up to date with the NEC. By following these guidelines, you can help ensure that EMT grounding in hospitals is safe, effective, and compliant with the NEC. It's also important to note the specific voltage levels in question. For example, Are we dealing with 120 volts, 208 volts, 277 volts, or 480 volt circuits? The voltage level can influence the selection of appropriate grounding methods and conductor sizes. In addition, consider the available fault current at the source of the power supply. This is the amount of current that would flow in the event of a ground fault. The higher the available fault current, the more robust the grounding system needs to be. Calculations should be performed to determine the appropriate size of the equipment grounding conductor and the bonding jumpers. The NEC provides tables and formulas for calculating these values. Another factor to consider is the presence of sensitive electronic equipment. Hospitals often have sophisticated medical equipment that is susceptible to electrical noise and interference. A properly designed grounding system can help to minimize these problems and ensure the reliable operation of the equipment. In some cases, it may be necessary to use special grounding techniques, such as isolated grounding receptacles or shielded cables. Also, think about the potential for electromagnetic interference, or EMI. EMI can disrupt the operation of electronic equipment and cause inaccurate readings. A well-designed grounding system can help to reduce EMI by providing a low impedance path for unwanted currents. Furthermore, consider the environmental conditions. Hospitals can be harsh environments with high humidity, temperature variations, and exposure to chemicals. The grounding system must be able to withstand these conditions without corroding or deteriorating. Corrosion-resistant materials should be used for all grounding conductors and connectors. It's also important to have a system in place for periodic testing and maintenance of the grounding system. This will help to identify any problems early on before they can lead to a safety hazard or equipment failure. Testing should include visual inspections, continuity tests, and ground impedance measurements. The results of the testing should be documented and kept on file. Regular training for electrical personnel is also essential. Electrical workers should be trained in the proper grounding techniques and procedures. They should also be aware of the potential hazards of working with electrical systems and how to avoid them. The training should be documented and updated regularly. Hospitals should also have a written electrical safety program. This program should outline the procedures for working safely with electrical systems, including grounding and bonding. The program should be reviewed and updated annually. By implementing these measures, hospitals can help to ensure the safety of their patients, staff, and visitors and the reliable operation of their electrical systems. Remember that electrical safety is a shared responsibility. Everyone who works with electrical systems should be aware of the potential hazards and take steps to protect themselves and others. In addition, consider the impact of any modifications or additions to the electrical system. Any changes to the system should be reviewed by a qualified electrical engineer to ensure that they do not compromise the grounding system. The engineer should perform calculations to determine the appropriate size of the equipment grounding conductor and the bonding jumpers. They should also verify that the new equipment is compatible with the existing grounding system. It's also important to consider the coordination of the overcurrent protective devices. The overcurrent protective devices, such as circuit breakers and fuses, should be coordinated to ensure that a fault is cleared quickly and safely. The coordination study should take into account the available fault current and the impedance of the grounding system. In some cases, it may be necessary to use current-limiting fuses or circuit breakers to reduce the available fault current. Furthermore, think about the use of surge protective devices, or SPDs. SPD can protect sensitive electronic equipment from voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at any point where sensitive equipment is connected to the electrical system. The SPD should be properly grounded to ensure that they can effectively divert surge current to ground. Also, consider the use of uninterruptible power supplies, or UPSs. UPS can provide backup power to critical equipment in the event of a power outage. The UPS should be properly grounded to ensure that it can provide a stable and reliable source of power. The grounding system for the UPS should be separate from the grounding system for the normal power supply. Moreover, consider the use of harmonic filters. Harmonics are unwanted frequencies that can be generated by electronic equipment. Harmonics can cause overheating of electrical equipment and can interfere with the operation of other equipment. Harmonic filters can be used to reduce the level of harmonics in the electrical system. A harmonic filter should be properly grounded to ensure that they can effectively filter out the harmonics. In addition, consider the use of power conditioning equipment. Power conditioning equipment can improve the quality of the power supply by reducing voltage fluctuations, noise, and other disturbances. The power conditioning equipment should be properly grounded to ensure that it can effectively condition the power. Finally, remember that the NEC is not the only standard that applies to electrical installations in hospitals. Other standards, such as those published by the NFPA and the Institute of Electrical and Electronics Engineers or IEE, may also apply. It is important to be familiar with all of the applicable standards and to follow them carefully. By following these guidelines, you can help ensure that the electrical system in a hospital is safe, reliable, and compliant with all applicable codes and standards. The key is to understand the specific requirements for each area of the hospital and to design and install the grounding system accordingly. This requires a thorough understanding of the NEC as well as the specific needs of the hospital.